Waterloo, and she's going to talk about measuring the ages of quiescent galaxies. You're muted, Kirsti.
All right, sorry, trying to figure out the Zoom controls. So hi, my name is Kirsti, and I'm just going to talk about comparing the ages and star formation histories of the quiescent galaxies in the GO-GREEN sample, comparing between galaxies in field and cluster environments. So first of all, following on with the talks previous, one of the main ideas of GO-GREEN is to trace the formation and evolution of the galaxies from their stellar populations. And how Remco and Lindsay have done this, and how many other studies have done this, is look at instantaneous, or in air quotes, instantaneous galaxy properties over several different redshifts. So looking at a population of galaxies at higher redshift and connecting them to a different set of galaxies at lower redshift, and assuming that the higher redshift galaxies are progenitors of the later galaxies. And this has been very informative, but there's a second way that you can sort of trace the formation and evolution of galaxies. And that's kind of the focus of what I've been doing with the GO-GREEN sample. So instead of using different populations of galaxies over different redshifts, I try to reconstruct the star formation history from just individual galaxies based on their integrated luminosity. And I provided a small cartoon here to try and explain how this works. So if you look at one particular galaxy, and you assume that it's made up of some distribution of stars with different properties and ages, each of those stellar populations will have a different SED, which is the spectral energy distribution. And this SEDs will evolve depending on the properties and the age of those stellar populations. But what we observe when we look at one of these galaxies and just put a single slit over it is just that combined or integrated luminosity function. So the idea is, from this integrated luminosity, is to infer the weighted contribution of all of the different stellar populations that make up a galaxy and try to reconstruct the star formation history of that galaxy. So if you have an integrated luminosity that more reflects an older stellar population, you know that the bulk of its star formation was at early times. And this comes in handy because there are differences in the SEDs over time. So just another cartoon showing some of a set of example GO-GREEN filters, where just with broadband photometry, you can try to capture the overall evolution in the shape of the SEDs as a function of their age. But there are also significant differences as a function of time on small scales. So just highlighting the rust frame optical region here in this green box, you can see that over small wavelength scales, there is also additional evolution, or there's other noticeable evolution. So a galaxy or a stellar population that's quite young, maybe half a gigayears, will have very strong Balmer absorption lines, where these cartoons are just showing the evolution and the absorption features. But by the time that they're around 60 years old, those Balmer absorption lines aren't as relevant as other things such as calcium, K and H, or G band. So what we want to do is use the differences between the SEDs as a function of age to figure out how much of the integrated luminosity is made up of stellar populations of the different ages. And something that's relevant in the next slide that I want to point out here is you can see that a stellar population of half a gigayear is noticeably different than one that's 1.5 gigayear. But there are much more subtle differences once you get to older ages. So 3 gigayears will look more similar to a stellar population of 6 gigayears. In reconstructing the star formation histories from the integrated luminosity, you want to figure out the weighted contribution of stellar populations of different ages. So you can use the fact that the SEDs evolve as a function of time and that they look different depending on their age. So broadly on long wavelength scales, you can use photometry, where these gray lines here show several different example filters to capture the overall shape of the SEDs and distinguish young populations from old populations, but there are also significant differences on small scale. So the green region just highlights kind of the optical region, where you can see that the absorption features change from being dominated by Bulmer lines when the stellar population is quite young to more evolved features later. And the fact that the stellar populations have different SEDs, at least you're able to tell apart stellar populations that are quite young between ones that are moderately young, so half a gig year and 1.5 gig year look substantially different. But older stellar populations become much more similar in their SEDs, so it's less, you're less able to distinguish a population between 3 and 6 gigayears. So that's one of the challenges of this technique. Okay, so just highlighting some of the problems of the star formation fitting technique. So the fact that stellar populations that are older are difficult to distinguish from each other. There's also a problem where if you have recently formed stars, those young stars will outshine your older stars that could form the bulk of your star formation, of your stellar mass rather. So as an example here, I'm just showing the star formation history as 2 declining exponentials, where in all cases, the majority of your stellar mass is formed at early times, but your integrated luminosity can look quite different. So even though in this case of the magenta star formation history, a very small fraction of the stellar mass is formed recently, the UV luminosity, so all of this blue light here, is totally dominated by those young stars, and even into the optical region. So for this reason, for our work, we're going to focus on quiescent galaxies to avoid this issue. So we want to look at just very evolved, not recently forming stars, or not recently forming galaxies. There are also problems between trying to distinguish different galaxy properties, because some of them will have similar distortions to the shape of the SED. So dust, age, and metallicity will all simultaneously redden your SED, so you have to consider all of them together when trying to constrain the star formation history. And lastly, something that's been talked about in recent years is the fact that if you constrain your star formation history to have a particular shape, such as a declining exponential, which is a convenient form because, you know, quiescent galaxies, you kind of expect to have this sort of smooth declining evolution in the star formation rate. But if you fix your star formation history to have a particular parametric form, you can bias the shape and then bias the overall age that you would measure in fitting that spectrum. And there's 2 papers here that talk about this in quite a bit of detail, and I encourage you to look at them if you're interested in that particular topic. So, but this is the motivation for, in our work, we use non-parametric, which are more or less free-form star formation history models, as opposed to some sort of parametric form, like a declining exponential or double power law, which are also used in other works. Okay, so star formation histories have been measured quite a bit in the past few decades, but it's quite a challenging technique, particularly because of the number of dimensions that you need to fit all the different parameters together, as well as the amount of data that you need. So historically, you can do an alternative technique, which is instead of fitting all of the spectra together, you can just fit individual spectral features. This is particularly useful when you have very high signal-to-noise spectra, which is available kind of only at low redshift. So sometimes these are called Lick indices. And from these individual spectral features, if you measure their equivalent width, you can build grids in parameter space. So here's an example of comparing 2 different Lick indices, where you have a grid of expected galaxy evolution as a function of age and metallicity. So in this case, Thomas 2005 did this for a number of galaxies, and you get a sense of their relative age and metallicity. But you're more interested in galaxies at high redshift, where your age precision is a little bit better because your galaxies are overall younger. But the problem is that the signal-to-noise is lower. And this is the reason that star formation history fitting is better suited to the high redshift. You want to use all of the information available in order to get a good estimate of the star formation history and the average age. And we can take advantage of significant advances in the computational techniques and then the statistics to do this process. Okay, and then just before moving on to how we do this with GoGreen, I want to highlight some of the consensus, some of the points of consensus from these lower redshift observations. So the first is that there's mass-dependent evolution. And this is to say that the star formation rates of the most massive galaxies tend to have peaked at earlier times than lower mass galaxies, which is to say that they formed their stellar mass earlier. And that's what's shown in this cartoon from Thomas 2010, where this red contour here shows that this is the dominant epoch of the most massive galaxies in that they formed most of their stars during this time. But as you go to lower mass galaxies, the star formation happens later, as well as over much more extended amounts of time. Oh, shoot. And then just recently, kind of in very low redshift, there's an era of rejuvenation or late star formation. So a second point of consensus among fewer surveys is a comparison between the quiescent galaxies between cluster and field galaxies. And in doing this comparison, they find that the early type galaxies and clusters are typically older than their comparable galaxies in the field. At redshift of 0, they find an age difference around 2 gigayears, but some of that is likely due to late star formation, so either rejuvenation or frosting, depending on your preferred terminology. But at higher redshifts around 1, the age difference is closer to half a gigayear, but with relatively high uncertainties of half a gigayear. And then these comparisons themselves are typically between very few galaxies, very massive galaxies, and relying on those Lick indices, or just based on star formation histories with only photometry, which are less constraining than including the spectroscopy as well. So this is a great position for GoGreen to be in because we have this huge sample of galaxies over a wide range of masses. We have the photometry as well of the spectroscopy, and our signal to noise is fairly good. Okay, so what I do in this project is identify the quiescent galaxies in GoGreen. So we want to focus on the spectroscopic sample, and we use the rest frame UVJ colors to identify just the quiescent galaxies. We also looked at other tracers of quiescent versus star forming, but the UVJ colors were pretty good here. So this gives us a sample of 224 cluster galaxies and 110 field galaxies. So for each of these galaxies, we can combine the photometry, which is shown here as green points, with the rest frame optical spectroscopy, where the wavelength region is shown kind of in this gray box and zoomed in this lower plot, to fit different models of the spectral energy distribution corresponding to different star formation histories. So for a set of parameters, you can build models of your data and fit them to your spectrum and your photometry simultaneously. So what's shown here in this black line is the best fitting template, or the maximum a posteriori template, which fits our data well. And then doing this with MCMC, we can build posteriors for all of our parameters, where we include things like redshift, dust opacity, stellar metallicity, as well as a few parameters which control for systematics in our data. But what we're primarily interested in is recovering the star formation history of this galaxy. So in different bins of look-back time, we fit for the relative star formation rate as a function of that time. And in using the posteriors from this MCMC, we can do a weighted average to get a posterior of the mass weighted age of that galaxy. And then here's, I just wanted to highlight, this is what we kind of meant by a non-parametric star formation history model, where we're not explicitly fitting a declining exponential form, but this is kind of more of a step function with a prior between each adjacent star formation history bin. Okay, so just a few slides on the results. what I've shown here is the mass-weighted age in units of cosmic time. So instead of having the mass-weighted age on the y-axis, we've just subtracted the age of the universe when that galaxy was observed, and then plotted it here against stellar mass. So on the top, these are all the field galaxies, and below is the cluster galaxies, where the contours show the combined posteriors of all the samples in each environment. And then the individual points, the circles and the diamonds, just indicate the 50th percentiles of those individual posteriors. So the main thing that I want you to notice here is that already you can kind of get a sense of the general result of this work, which is that looking at the contours, the cluster galaxies tend to be forming, or their mass-weighted ages tend to have been earlier than the field galaxies. So the mass-weighted ages exist over a much more, a larger variety of times in the universe than the cluster galaxies. So you could say this as the average population of cluster galaxies is older than field galaxies. A second thing to note is that these diamonds indicate galaxies which have had more than 10% of their mass formed within the last gigayear, which is to say that they're overall quite young for quiescent galaxies. And there's a much higher fraction of them in field galaxies than there are in cluster galaxies. But in order to do a systematic analysis between these two populations, instead of just qualitatively assessing these contours, what we do is compare the galaxies in bins of smaller mass range, so here just 0.1 degs. And then we compare their cumulative distributions. So here I've just plotted the cumulative distribution of cluster galaxies versus field galaxies, and measured the offset from the horizontal here, which has units of time, and then bootstrapped those populations to get a handle on those uncertainties, and build posteriors of the difference between the formation times of field galaxies and cluster galaxies. So the difference here being positive means that the formation time of field galaxies is later than cluster galaxies, or respectively that cluster galaxies are older. So then we combine all of these finer mass bins to broader mass bins, where this black line here shows the combination for the full mass range of our sample, where this kind of is the quote of our result, where cluster galaxies are typically 0.3 gigayears older than field galaxies, or at least less than half a gigayear, but within 1 sigma, still consistent with 0. And what we do then is look across broader mass ranges, and we can see that this result is dominated by the majority of our sample, which have moderate stellar masses, but the difference is a bit smaller at the lowest stellar masses in our sample or the higher stellar masses in our sample. So just in the last few minutes of this talk, I'm sorry, I lost track of time, unfortunately. But what does this imply about the star formation histories of field and cluster galaxies? So Remco talked a little bit about the toy models that we've been playing with the Go Green results. And that's the context of this Head Start model. But before that, I just want to address this fiducial model, where we can consider environmental quenching to happen after a galaxy falls into a cluster. So here in this model, you have two competing modes of quenching. You have this mass quenching, which is related to your star formation rate, and then you have environmental quenching, which is related to how recently that you've joined a larger halo. So because mass quenching dominates when your star formation rate is high, this means that the majority of your quenching by this mode happens at early times in the universe. But as you continuously assemble your larger halos in your galaxy clusters, you're continuously building up your population of environmentally quenched galaxies. So the consequence of this model is that if you exclude any sort of pre-processing in your cluster environments, your field galaxies are going to be older than your cluster galaxies. Sorry, this should say your quiescent field galaxies are typically older than your cluster galaxies. And that just is a consequence of the fact that your mass quenching happens at earlier times, where you're continuously adding to your population of quiescent cluster galaxies. So as an alternative, you can consider this Head Start model, where instead of having the second mode of quenching related to the environment, you can consider just the fact that galaxies that end up in clusters simply formed earlier and hence are older overall. In doing this, you can make predictions of how much earlier the cluster galaxy should have formed to reproduce either the quenched fractions or the difference in the mass-weighted ages. So we've done a little bit of a different modeling approach than REMCO. So we've constrained the difference in formation times within 1.7 gigayears based on the quenched fractions. But this doesn't jive with the fact that the ages kind of restrict the difference in formation times to less than 0.75 gigayears. So there's still work to be done here because we haven't yet found a model, at least a toy model that's simple enough to pull together all of the different results from our Go Green analysis. And then, yeah, just want to say thank you for joining again, and then just a few slides here summarizing the results.
Great, thank you, Kirsti. Excellent. I think there's lots of stuff there that, and there's a couple questions in the chat, but we'll come back to that during the discussion.